Q is standing for the field of a fermionic field, Q bar, etc. And the axial current, again on the U-5 current, or if you could do probing with gravitons, of course, you would start probing TMD, you would start probing that sort of currents. So that's things that for quarks and gluons, and of course gluons don't show up in a current that couples to the photons, and ZW, so essentially you see this, but in the TMU, if you could measure it, gluons would show up. This will again also come back to some properties of the PDFs and the fragmentation functions. Okay, so the next step what you would like to do is get to these objects themselves. And so one of the things which already, as I said, is say, we know the currents. But nevertheless, then there is a combination of currents that play a role. Everything that couples to the photon is found in a certain process. And so it's more, when we go to the quarks and the anti-quarks, more or less infinity. And the answer is yes. And it requires the thing that requires is essentially that you do high energy experiments, do them inclusive, essentially break up the proton and break up the proton sufficiently such that the intermediate states that you produce are essentially a complete set of states, and then you have a matrix element proton going to a complete set of intermediate states through an operator, and you have to square this in the scattering process, and what you then find is again a forward matrix element if this intermediate state can be removed. And that intermediate state being removed essentially says it is complete, and so you integrate over it, and this is what is typically done in inclusive measurements. So they should be sufficiently high energy such that they completely cover the breakup spectrum, say, of a proton. And again, the Lagrangian is, no, that's the assumption in getting to PDFs and fragmentation functions, partial distribution functions, or you will hear the word PDF very often, FF, fragmentation functions, you will see this, PFF, parton fragmentation functions, then that will start playing a role. And then the basic thing of these lectures is, because the PDFs and the PFFs are a topic that Chunzo Manu is talking about. Again, somebody who I met a long time ago at MIT when I was a postdoc there. That was the first time we met. He will discuss these functions, and I will try to say, but there could also be a role for transverse momentum in that whole process. And now, of course, I haven't told you so far why the transverse momentum don't immediately play a role in PDFs, and that will then come. Questions at this point? General questions, naive questions, questions that you never dare to ask.
In your conversion of that local operator,
Sorry?
I think it's 9 base.
8?
8. In your conversion of that local operator, why can't there be other terms?
In this one?
Yeah.
Oh, why can there not be other terms? Simply because you know that this operator, for instance, or that this is used, there can be other terms, very good, there could be other terms. Although in this situation I'm not completely, I have to think about it. But in the, you have to say, first of all, these are momentum states, so they are plane wave states. You use a plane wave state, say they are eigenstates of the momentum operator. That's used to get this. Then this operator has certain problems, and it is used, that's what I forgot to say, so very good question, and it will be used in a process or in an interaction that we know conserves, for instance, parity. If parity would not be conserved, you might be needing other terms in it. So the number of form factors, and we will see the explicit example later, in the number of distribution functions or the number of fragmentation functions that is going to play a role is also such a parameterization, and the limiting factor is the fact that you are looking at interactions that where parity is a good symmetry, where charge conjugation is a good symmetry, so particle-antiparticle is a good symmetry, and time reversal is a good symmetry. You're looking at those theories, and QCD is basically, forget about possibilities of anomalies and that sort of things, but the basic QCD, as used in strong interaction physics, has the symmetry that parity, charge conjugation, and time reversal are good symmetries. Even some of you may say, but now later on he's going to talk about T-odd functions. That's the Mulders function. That is a T-odd function. T-odd. So time reversal, it changes sign. Is time reversal then not conserved? Already let me tell you at this stage. T-even and T-odd, the strength of it is that T is conserved in QCD, time reversal. Or just as parity is conserved, if parity is conserved, it is possible to have objects that have positive or negative. But that's only parity. So that's only when parity is, or in this case space inversion is a good symmetry, then there is a conserved quantum number parity. And so there is a possibility to later on have parton distribution functions that are T-even and T-odd because time reversal is a good symmetry of QCD. So if you want to look at certain beautiful small effects that are time reversal violating, you will need yet another PDF. And then you give it your own name. Now you have other people giving it a name. We didn't give it that name ourselves. So this is indeed a very good question. This parameterization, there's a lot of input in these sort of parameterizations. And I will go to the PDFs and the PFFs. Other questions? Now we are starting. Okay, so again, there's more information if the operator has more positions in it, if you want. And still is a forward operator. Then you would have much more. I mean, you could get rid of an overall factor. And essentially, that is non-local operators only depend on the difference, essentially, between the two. Because just as translation invariance is essentially, you know, translation invariance in quantum field theory tells you that the operator at point x is the operator at point 0, but then sandwiched on the right and the left with e to the I p operator x and e to the minus I p operator x. Should I write that down, or you remember that from your classes? Operator at x in field theory is equal to the operator at 0, and then left and right are e to the ipx, e to the minus ipx. I shall not write it down because I don't know where minus ipx is. That's perfect. But the e to the ipx and the e to the minus ipx on the left and the right, these are plane waves. So that's how you got this factor e to the I delta x in the form factor, when p and p prime are not the same. But this is forward, and then they are the same. So you see that you can shift any operator which is at 2 points, you can shift it if you give both points an additional position, so shift it over a certain distance. So that's why only the difference essentially is a relevant operator in a non-local operator. Now, where do you get non-local operators? Now, non-local operators, and particularly the beautiful one that we are going to use, are operators where you have two quark fields, or two fermion fields, or later on two gluon fields, or gluon field strength tensors, but quantum field theoretical operators at two different positions, and that is something which occurs essentially in, because then if you have two of these operators, for instance, just take the product of these two operators, psi back of psi, then you have an operator, put it between this thing, Fourier transform it, and then you notice that this thing indeed is something which brings p to, how can you write this in single matrix elements? Only when you see there's such an object, you have to put something in between, and then you get fine typical matrix elements. So down here. But I'll go back to this sort of, I mean, we'll see why we get this sort of structure. But I just here want to say on the structure of operators, non-local operators, for instance, those which made up of the product of two fields, like two fermion fields at different points. The overall point doesn't matter, so you can take minus y or plus y, or you can take 0 and y. I mean, you can shift it over x minus y over 2, and then this thing is going to be 0 and y, and it doesn't matter. So only the difference matters. But this difference, by putting in a complete set of states, and essentially having this integral is going to be, I mean, you put in a sum over x integral over all momenta, and this is going to be a delta function. This line, how the product of two currents, matrix elements of the product of two currents, is transferred into a non-local matrix element, is an exercise that we should do, if you haven't seen it. I think many of you have seen it. I mean, it's at the basis of deep inelastic scattering, and you write down something like, say, I have a proton, I have an electromagnetic current, it goes to anything, I sum over this anything, and then what you will, and essentially the momentum has to match, so you start in the other way, you say, this is what my cross-section does, and then you write it back into a non-local matrix element, and then you have certain non-local matrix elements. These non-local matrix elements are going to play an important role. So this is the sort of what I try to say is often you see a formalism where people start off, try to see to the basic things. This transformation of, say, the square of just some operator which brings two sets of states together, square it, is written as a non-local operator, but still between momentum states, with the same states. That's because you have eliminated some x. So this will happen when your photon hits a proton, excites it, and the energy is so high that the excitation covers the full spectrum, so you do it inclusively, you integrate over everything, sum over everything, then that's removed, and then you have again simple operators, simple in the sense that they may be made up of a product of fermion fields, or a product of gluon fields, or whatever fields or your object fields. And this product is then evaluated between momentum states, so go back to this thing, and those are beautiful things. And what we'll see is that they are essentially not anymore a global thing, but they provide a selectivity. And again, you can not fully grasp that here, but you may be seeing this if you do the exercise. It's, I think, the first exercise in the Van lecture, so you can find it and do it if you want. Okay, so this is then what turns out to be that such a matrix element that the difference becomes relevant, and difference becomes relevant and essentially tells you that in this case the photon Q is feeling a momentum P. And that we will rediscover in many other ways that distribution of fragmentation functions can be defined. And the picture is you have a hard Q, either space-like or time-like. So this is a time-space picture, space-time picture. There's a spatial momentum hitting a high-energy proton, and essentially there hitting a high-energy one, say, parton, say a quark. Photon can also have gluons, it feels quarks. And then essentially this thing, the quark scatters elastically, and that is able to absorb the momentum, and so this momentum goes into that momentum, everything fits, and essentially what you see is that you have a proton coming in and that something goes out in another direction, being hit by a hard Q. Or then a hard Q, now time-like, so that's produced when you have E plus and minus and annihilate, then you have a, say, a photon with high time-like momentum Q, and this high Q again can do, say, hit these things. That's just momentum conservation that only can work, at least for massless constituents, if they're heavy quarks. Of course, you have to take that into account, but otherwise, these things can only be along the light cone and essentially go out into two timeline directions, and essentially, that's essentially the flying apart in the center of mass, of course. This is then saying that you produce quarks and antiquarks in two opposite directions. That's what E plus E minus scattering does at high energies. And you have a two-jet situation. Of course, there can be later interactions, there can be emission of whatever, so there are follow-up processes, but this is the basic relation case. Okay, and experiments, of course, deep inelastic experiments showed that this picture beautifully works. Okay, so that's sort of for the introduction. Now let's get to more complex situations. And we see we don't break, or we is there a need for a break of 2 minutes, or
Up to you.
is there a need to get coffee and then come back in a few minutes?
Yeah.
Because I think I should stop at 11:30.
Okay, yeah, let's have a break for, let's say,
few minutes.
5 minutes.
5 minutes. Because you get your later break at 11:30.
Yeah, yeah. And also one thing, after this section, please, let's go to the lobby in the first ground floor to take the group photo.
Yeah.
So, thank you.